Hi, we're Team Interplanetar, an undergraduate rover team from Bangladesh University of Engineering and Technology, presenting the latest iteration of our rover Prochesta V4.0 for the next Anatolian Rover Challenge 2025. Team Interplanetar has been representing Bangladesh in different Mars rover competitions around the world since 2011. We started our journey with ERC with our Mongol E version 2.0 rover. Since then, Team Interplanetar has participated in many rover competitions around the world, such as the University Rover Challenge, European Rover Challenge, and IRDC. We took part in the International Planetary Aerial Vehicle Challenge, where we won the Innovation Award. We also achieved the 8th position in the ERC On-Site 2022 and 4th position in ERC Remote 2022. For the collaboration missions this year, our astronauts will be trained to assemble the rover from scratch within a certain time. They will also be trained to set up the communication system within a short time.
Our team's workspace is situated within the university's project lab. It serves as our central hub for team meetings and project collaboration. Within this space, each subteam has its own designated area, facilitating simultaneous work. Here we refine designs, construct and test subsystems, and assemble the rover. We operate our 3D printer for the in-house manufacturing of rover components. Additionally, we utilize various workshops for laser cutting, bending, and other various tasks. For testing purposes, we utilize both the project lab and the open spaces available on our university campus.
We have made every endeavor to minimize the weight of our rover, and it now weighs approximately 58.6 kg, including the science payload and communication system. Each wheel weighs around 4 kg, while the suspension and chassis together weigh approximately 14 kg. While the antenna is kept straight relative to the ground, suspension and chassis covers length of 1.05 meter, width of 1 meter, and height about 1.53 meter. We have used wheels of diameter 300 mm. In addition, the communication antenna adds 2.1 kg to the overall weight, and the manipulation system weighs around 10 kg, which may vary slightly depending on the specific end effector required for a given task. The manipulator can reach 1 meter above ground and 100 mm below ground. We have implemented a new science payload comprising drill and drilling platform of 4.3 kg, scooper and chassis respectively of 0.2 and 1.5 kg, where the whole payload is of length 343 mm with 260 mm along with adjustable height 490 mm to 1 meter approximately.
This year, a completely new chassis is designed and manufactured to reduce weight and ensure modularity. The chassis is made of stainless steel square tubes, which is TIG welded, providing strength while being lightweight. It provides more space for electronics, arms, and science payloads.
The suspension is made from stainless steel square tube. This year, we made a modification by shifting the link bar differential from the front of the chassis to under the bottom.
We implemented a 4-wheel rocker suspension mechanism to keep the rover lightweight. Wheels are attached to the rockers on either side of the rover chassis. Bar differential keeps the rover chassis balanced at an average angle between two rockers on either side, which allows the rover to climb over rocks and uneven grounds while minimizing the jerking of chassis, thus protecting sensitive electronic components inside. We tested the rover for traversal in extreme rockery terrain. Our rover can climb steep slopes and traverse through harsh environments. Rover can also drive over sandy grounds.
Last year, our rover was equipped with in-wheel planetary DC gear motor driven by BTS 7960 motor driver. This year, we are switching to sensored BLDC hub motors controlled by open-source STM32 motor drivers using an FOC algorithm. This setup will provide smoother control, consistent torque over varying RPM. The inbuilt Hall sensor will provide odometry data for accurate navigation.
The ARM board employs an L298N motor driver to control the DC motor responsible for the gripper's movement. Two stepper motor drivers are used to operate the stepper motors in a differential system of the roll pitch mechanism. A DC motor coupled with a worm gear is employed for base rotation, while two linear actuators control the shoulder and elbow movements. Three BTS 7960 motor drivers are used to drive these three actuators. To monitor the movement of each joint, an AS5600 MATI encoder is integrated. The system is controlled by a Raspberry Pi Pico microcontroller.
Centralized power distribution system that generates 5V, 12V and 24V buses. Our custom designed PCB is built to withstand up to 100 ampere of current. A power module is integrated to provide real-time monitoring of voltage and current. Additionally, a high current relay is included to shut down the rover in case of emergency.
Safety of the rover and our crews is our top priority, so we have installed an industry-standard kill switch to cut off the power from the batteries in the case of emergencies. When pressed, the kill switch cuts the power to all moving parts like arms and wheels.
This year's science board utilizes an Arduino Mega as local microcontroller chosen for its numerous I/O pins. Coupled with different motor drivers, our board can operate 2 DC motors for the movement of the science module and 1 for auger drill. A DC motor and a servo motor are used for sample collection in the sealed containers. Load cells and HX711 load amplifier modules are incorporated to measure the collected samples.
Learning from previous years, we have simplified the ARM design, and this lighter design is manufactured using TIG-welded SS square tubes. The 6-degree of freedom arm stands on a tightly integrated worm gearbox run by a DC motor, which provides base rotation. This worm gear reduces backlash of previous design.
This year, we have modified the previous end effector by replacing most of the plastic parts with aluminum alloy. This enabled us to make the roll, pitch and yaw mechanism 74% smaller in volume while still maintaining the similar strength. The end effector can push buttons, flip switches, plug in USB and type on keyboards. With the 360-degree continuous rolling, we can turn knobs and drive screws with a screwdriver. The arm can pick up objects from the ground, pull ropes, open and close latches and drawers.
For ARC'25, we have designed a compact yet powerful science module which is 34 cm long and 26 cm wide and a 7.5 kg payload capacity. A lightweight aluminum frame minimizes overall weight, while high-strength stainless steel is used in critical guides and moving parts, ensuring smooth operation. To achieve the science mission, 4 functions are performed consecutively. Those are drilling, sample collection, storing samples, and analysis of the samples. We have an auger drilling mechanism capable of extracting soil from the depth of 15 cm and collects them in a closed container. Manufacturing is under development. The containers can rotate to take different samples and measure weight.
For laboratory tests, we have used color-changing chemical analysis for the detection of organic materials in order to determine the presence or absence of life. Iron-formed phyllosilicates have been used for justifying our hypothesis. Rock sample analysis will be conducted with the help of 2 pi cameras. Habitability analysis will be conducted with the help of temperature, pH and NPK sensors.
At the ground station, we have a Linux-based system with ROS2 and communication system. The communication system allows us to connect the ground station's local machine to the rover's onboard computer. We also developed a graphical user interface which connects to the onboard computer of the rover with SSH and ROS2 master slave connection. The GUI controls the wheel's rotation, arm joints, and science tools. The GUI also shows the vital feedback such as latency, rover's position, and current joint of the angle of the arms. The communication system includes sector antenna and base station antenna. The sector antenna connected to the router allows us to operate the rover from multiple local machines.
The communication system between the rover and the ground station is based on a 2.4 GHz wireless link that allows for bidirectional data transfer. We use Rocker M2 access point routers on the rover and the base station. The base station router has a 15 decibel sector antenna with a 120-degree coverage that is placed facing toward the rover. The rover has an onboard 10 decibel omnidirectional antenna that allows the rover to communicate from any orientation. These are high-gain antennas that ensure no line-of-sight communication for up to 1.5 kilometers. The wireless link is used to transfer control commands, camera feed, and sensor data between the rover and the base station in real time.
This year we are using ROS2 to develop the communication architecture. ROS2 allows seamless data transfer among all the connected devices within the network through topics and services. The base station and the rover share control commands and data through specific ROS topics. The onboard computer of the rover sends the control commands to the microcontroller accordingly, and the actuators are operated. Similarly, the onboard computer sends sensor feedback data to the base. We are using WebSockets for streaming the video feed from the rover to the base station with low latency. A separate user interface for the camera feed makes it convenient for the operator to monitor the rover throughout the task.
Here is some demonstration of our rover performing tasks similar to ARC'25. For the first mission in Mars field, our rover excels in scientific tasks like soil collection, chemical analysis, and sample tube delivery. In the second mission on the far side of the moon, the rover will navigate autonomously between several obstacles with precision. For the third mission on the moon field, the rover efficiently navigates between locations, undertaking maintenance tasks crucial for mining operations like picking up and transporting objects, pressing keys, operating joystick, pulling ropes, and sliding drawers. Lastly, in the fourth mission, the rover maneuvers through the Mars field at night using cutting-edge vision systems currently in development.
We are thankful to our sponsors and partners for their continuous support. Thank you for watching. See you in ARC.